All right, we will get started with the orbital debris panel now. As more satellites are entering low Earth orbit and space travel becomes more frequent, orbital debris has come to the forefront of our minds as an imminently worsening issue that seems to have no clear and easy solution. Technical, legal, and regulatory talent are banding together to characterize and design solutions for mitigating orbital debris in LEO. Please welcome our panelists, experts in these areas, and our moderator for the orbital debris panel, Dr. Doug Beeson.
Good morning. Hopefully everybody is awake enough to think about everything from policy to technical details here. But we're just going to go ahead and kick off, and we're going to do this alphabetically. We're going to have Kirsten speak first. And she's a very well-known program manager, and her bio is in the book as well as everybody else's. So Kirsten.
Thank you. I have some charts. Can we switch over to those? Terrific. So good morning. Given the range of experts we have on this morning's panel, I'm planning to give an overview of the technologies that address the problem of orbital debris. One of the key questions that was put to the panel was, what technologies must be developed to interact with uncooperative space objects? This question comes at the problem from the demand side. So the Tory group recently did some work to look at what technologies are nearing maturity and could be deployed in the near future. So we took more of a supply side look at the technology landscape. So our main purpose in doing this was to look for the low-hanging fruit in terms of the technologies that are most near maturity and could be deployed into industry. So in the next few charts, I'll give you a quick overview of our analytical framework and some of our key findings and takeaways. So we tried to bound the problem. Obviously, there are a lot of orbital debris concepts out there. We focused on mid to high technology readiness level technologies. We focused on those technologies that are 4 through 9, so tested in a laboratory environment through successful mission operations. The other dimension that we tried to bound the problem was looking at primarily domestic technologies. Those are really most of interest to government agencies. We did keep an open mind and looked at other lower TRL technologies or international organizations working in this area if we thought they were particularly notable. In talking about technologies for orbital debris, you really have to kind of set up some definitions. So the definitions that we looked at, we adapted the definitions from a recent RAND Corporation study on orbital debris called the Catcher's-Mitt study. And so we defined debris mitigation as actions that slow or prevent the future growth of orbital debris, and debris remediation as actions aimed at reducing or eliminating the population of existing debris. Paired with that, we had to look at the method for debris remediation or mitigation. So we looked at active methods, which require attitude control. This increases the system complexity and requires additional mass and volume. We also looked at passive methods. So these rely on natural forces to accomplish deorbiting. So given those definitions, we had 4 potential categories of technologies that we looked at. So active mitigation, passive mitigation, active remediation, or passive remediation. You'll notice that last one is not up there on the chart because we didn't come across any technologies that met our criteria in that particular grouping. So in the area of active mitigation, the technologies that we examined are chemical propulsion and solar sails. So chemical propulsion uses propellant to move the debris up to a higher graveyard orbit or lower the orbit to where atmospheric drag can take effect and remove the debris. Solar sails, they use the effects of atmospheric solar radiation pressure to create thrust and propel an object either to that a graveyard type orbit or to lower its perigee and deorbit the object. There are some other propulsion technologies that we looked at, and those are in the active remediation category. So the organizations working in this area, they are mainly working on mid-TRL technologies. So in the passive mitigation category, we had several groupings of technologies. Some of my fellow panelists have some technologies in this area. Electrodynamic or drag tethers, those use kilometers-long cables or a flat wire. The cable is conductive and uses the Earth's atmosphere to create a force that reduces the velocity of the debris. Moving on to mechanically deployed drag devices, these are drag sails and balloons. So a drag sail uses a lightweight, thin membrane to increase cross-sectional area, and then uses atmospheric drag to deorbit the object. Another concept is balloons, also uses a small amount of gas to inflate the balloon to a size of tens of meters. This also takes advantage of atmospheric drag to deorbit the object. Quite a number of organizations working in this area. They are working on mid to high TRL technologies. There are a whole slew of other organizations that are working on lower TRL technologies, so a lot of activity in this particular grouping. The third and last category is active remediation. The two kinds of technologies that we looked at are propulsion plus grasping. So this uses a satellite to approach the orbital debris object and then uses a capture mechanism such as bags, harpoons, nets, robotic arms, tentacles, tethers, or even tugs to grab the object and deorbit it. Electrodynamic propulsion with the grappler. This also uses a conductive tether to propel the satellite close enough to grapple the debris object and then remove it. So So what's particularly interesting about this area of technology are the capture mechanisms, but those right now are very low and not very mature. Low TRL technologies, they're not particularly mature as of yet. So the organizations working here are working on mid-TRL concepts, and there are many others working on lower TRL technologies. So our key takeaways in this area include various passive methods are effective for small low Earth orbit satellites. Active methods are the primary means for eliminating debris in GEO, both for mitigation and remediation. And as I mentioned, the capture mechanisms are currently low TRL. The technologies we've been looking at, they need to be considered as part of a systems solution that includes space situational awareness. And then this mix of domestic and non-US organizations in the community are working on various technologies and concepts. So the bottom line is a lot of promising technologies, but there are really few, if any, high benefit, high TRL options that are ready to be infused into our work. This is just really a brief overview of the technology landscape, and there's many other components to the discussion. I look forward to discussing further.
Well, great. Well, thanks, Kirsten. Well, thank you. And next, we're going to have Dave Barnhart, Program Manager at DARPA. And by the way, what we're doing is we're running through the panel members right now so that we can give all of us an overview of our take on orbital debris. And then we'll open this up for questions after a quick panel discussion. And as Dave is getting ready, just want to say that this problem of orbital debris was really not taken seriously until about 15 years ago or so. And I can distinctly remember over 20 years ago, one of my colleagues in fact, he was a professor at the Air Force Academy, had actually done his PhD thesis on orbital debris. And at that time, it was something that nobody could even imagine that we would have this type of problem. So with that, David?
Okay, hopefully this will work. Great. Hey, thanks very much. Thanks, Doug. Thanks to the distinguished panelists that I'm on here. First and foremost, I work for DARPA. There is no official position on orbital debris. Please do not throw me under the bus by me being here. Second and most importantly, the disclaimer at the bottom says, shoot the messenger, do not shoot the organization the messenger comes from. So just let everybody know. Context is important, acknowledging work that was done. There is, as was identified by Kirsten, and there will be an arm wrestling match that will occur about whether or not this was a DARPA NASA-sponsored activity or a RAND study, because I've heard many different ones. The individual's name who's on this is Wade Pulliam. He was a program manager at DARPA. DARPA and NASA sponsored a joint activity that occurred with NASA. JC, Robert Johnson. It was really cool. I got a chance to go to it when I wasn't at DARPA at the time. But it is I wouldn't call it a seminal work. I thought it is a point in time. But it's really good. I'm acknowledging things that have been done by other PMs and folks at DARPA that I will draw upon to show and elucidate my story this morning. So from that, a problem that we are here to discuss, we all know it. It was sort of publicized as the K syndrome, runaway things that might occur. This is an actual chart that came from that report specifically. It also identifies the possibility to mitigate the potential runaway probability of multiple debris that occur. So you can see that in this particular case, up and to the right means things are getting out of control. What you want to do is bring that line down to the right if possible. So what the study recommended was, and this was just one recommendation, let me be very careful about that, one recommendation, hopefully NASA may have others, is if you were able to remediate 5 large objects in space per year or per some annum, that you might be able to stabilize the predictive probability of populations of potential things that would cause debris to affect that K syndrome approach. Right? So that was one recommendation. My job here is to get you to think differently. What if we could rethink the phrase remove objects to mass usage? All right? Okay, well, how? Well, you got to have some gimmick if you're going to do that. So let's see if we can get this to work. Please bear with me here. Biology shows a bit of inspiration.
Biologically inspired. Like cells, satellites aggregate and will conform to multiple payloads, providing powerful, redundant systems at a fraction of the cost of traditional satellites.
Okay, so that does much better job than an engineer standing up here and yakking to you. The whole concept that we came up with, the Phoenix project that I'm most familiar with, was to think about the value and mass of space differently, completely differently. So if the traditional mass had a particular specific cost to it, and that's broken up between the things that are up there, payload, bus, you got to pay for operations, you got to pay for launch, how might we affect the equation of that cost? So we concentrated specifically on the bus. How do things like that occur in Earth? Well, one methodology is that you actually create multiple manufacturer modules. We have on-demand transportation, FedEx, UPS, DHL, and then we have the ability to utilize high automation in terms of robotics to be able to put all kinds of things together for high-volume, low-cost manufacturing. Is there a simple way or a similar way to think about it in space? In Phoenix, what we did is we came up with a completely new construct about what a satellite is, and you just saw the basic element we call a satellite. We also thought about how do you create the FedEx to space capability, simple name called a pod. And then the last piece was, how do you put things together if you're able to deliver a FedEx box to space and you have to have a mechanic to put things together? Well, then you need robotics and some sort of service or tender. The goal was 10x reduction in the cost of that specific dollar value per kilogram. That was the point, right? It's interesting that the cells are being built right now. I brought some with me. I can show them after this. I don't want to take them out. We don't need to have pictures taken of them, but they're in pre-production as we speak. There are two companies that DARPA is actually funding to go off and build these things. There is also a company that's looking at production. How do you translate a single R&D activity from a pre-production stage to production to meet the cost numbers? We are going to fly next year. We already have a flight that's been paid for, bought, manifested, and ready to go to prove the construct of this brand new morphology of satellites. And we are funding a space factory, in essence, to be able to continue to proliferate this kind of a concept. What's interesting is the satellites were specifically developed for the original purpose of Phoenix was to repurpose geostationary satellites whose mass and value was 0 into something that was useful. The original precept of the satellite construct came around an application that was useful for us to demonstrate and exercise to push the technology boundary. In this case, we were going to resurrect, in essence, an aperture, which people think of as really low mass, probably doesn't cost that much, but the cost to get it up there and to put a 2,000 kilogram thing next to it had already been paid for, and now it was not doing anything. So was there a way to potentially put that together with a new construct? The interesting thing that came out of this, the discovery we came to, was you can come up with all kinds of different configurations if you have the ability to assemble spacecraft that we think of as monolithic devices in orbit. Fascinating construct, and this is one of the more interesting things. When my colleagues get up in the chair next to me, the right-hand picture on the right-hand side here, keep that in mind. Everything is linked, or could be potentially linked. There's a seed there, guys. It turns out the robotics to assemble the cells are in work, and they themselves were cellularized. Let's again see if we can get this to work. We are demonstrating as we speak the ability to utilize robotics in construct with a cellular architecture and morphology to put them together. Haven't solved everything yet, but we absolutely are working toward that. And I want to put a shout out here. Well, we'll stick with the same one, guys, in case we get ourselves stuck. I'm going to put a shout out here to another individual that created an object, created a cellularized robotic who is in the audience. And I'll embarrass him a little bit, Dr. Peter Will. If you're interested to see him, he created something called conformal robotics. What you're seeing is something that he did many years ago. I was not able to get publicly released. The cells of robotics that, through his inspiration, we've actually created and are building. So in essence, we have cellularized the contract of the spacecraft, as well as the devices to put them together on orbit. Fascinating construct. I won't let it play very long because there's a bunch of other smart folks that need to get up, talk. This is all great. Dave, this is wonderful, cool technology, but what are you going to do about it? I spent half of my time, believe it or not, as a DARPA PM, arguing over value proposition. And I would argue with you that that's the one thing that we have to address relative to what we talk of in terms of debris. The picture you see right there is a traditional value proposition layout in terms of cost, sunk cost, non-recurring engineering, as well as quasi-revenue that is typically agreed to or executed from a government standpoint. 8 years. See the length of time necessary before you get it all. Thanks very much. The Phoenix approach, what we tried to do was to change the temporal nature of the investment such that the whole curve would change. You get things up there much faster, and you incrementally build them or create them over time. So you use the construct of assembly, both in terms of the actual use of the mass as well as cost. But as it turns out, space is three-dimensional. So should not be the value proposition be three-dimensional as well? This is very crude. I apologize. I was PowerPoint cowboying engineering last night trying to lay this out. As it turns out, you can add another dimension to essentially what is happening to the value proposition. The original one is there. You can augment things if you have the ability to assemble them in orbit. You have the ability to add new missions, which means new value and new revenue streams, and you potentially can do other things that you hadn't thought of. It's a three-dimensionality proposition if you can actually achieve this. Okay, so What does all this mean relative to debris? I go back to this very first chart that I showed, the picture, 5 objects, cutting down the possibility of the case syndrome occurring. These represent things that have fallen to Earth that are called debris, but there's an order of magnitude more that are on orbit. If you think differently about what you could do with mass, and you're able to repurpose things that are on orbit that we think of as debris, but they might actually be purposeful and useful, you could completely potentially change the value proposition of what we're talking about, even to the point that you begin to think about now you've created the industry to allow you to assemble things or to move things around, even to the point that I know there's some other folks in here talking about asteroid mining. So a very short presentation to give you, again, to think differently about the construct, and my takeaway is economics is key. If you can find a way to make money on debris, to make money on things, the mass that's up there, that would change the game, and that would essentially enable us to go forward. That's it. Thanks.
Okay, well, thank you, David. Next, we have Joe Carroll, president of Tether Incorporated.
Let's see, how do I control the, great. Okay, good morning. I've been involved in the space business since 1982, so 32 years, just coming up on half my life. And about a year or two, I can't remember exactly when I met Don Kessler, but I very quickly got religion on the subject of orbital debris, because if you're interested in using tethers in space, the collision cross-section with the tether is not the width of the tether by its length, but the width of the objects you can run into, which may be several meters, by the length of the tether. So I began to take this problem very seriously, and I've watched the trajectory of interest rising on this. I don't, can you get my, yeah, okay. I'd like to add to what you said about economics being key, and debris is a resource, okay, among other things. 2,200 tons in low Earth orbit alone, okay. There's more than 10 tons a year of stuff leaving the space station that if you wanted to recycle, you don't even have to capture it. It's docked to the station, and it's going to re-enter and burn up. If you run out of that stuff, then I can deliver 50 or 100 tons a year of debris to the station. I would like to suggest that the barely extraterrestrial materials, which are leaving space station, is the place to start thinking about Phoenix program types things, because you don't have to go get them. They're there, okay? Beyond that, I can deliver other stuff, but start where you've already got the stuff there, okay? So, this presentation is available, if you go to the speakers page, it's apparently available online. I've got 18 slides, I'm only going to show 10. The last slide in the backups is bibliography. If you want to pursue any of the things that I mentioned more, go there, okay? And most of those references are online, so you can look at those directly. So, let's see, next. Terminology. There are various ways to slice and dice the problem for different purposes, and I think that cars, hubcaps, and shrapnel is a very useful one, and I'd like to explain that. I'd really like to encourage people thinking about it in this term. Most of the objects in space, most of the mass, and my focus is going to be low Earth orbit. A lot of it also applies to GEO and other orbits, but the problem is much worse in low Earth orbit, and I'd like to focus on that. Most of the mass and most of the target area for collision is tied up in intact objects, okay? And until recently, the so-called Kessler syndrome, which is not exactly what Don pointed out to be the problem, is that fragments that are tracked, many of them have enough mass that if they hit a car, they will shred it and make more hubcaps. And right now, the tracked fragments roughly outnumber the cars about 4 to 1, so hubcaps in cars is a kind of useful way to remember it. Over time, the ratio of hubcaps will rise, but right now it's roughly 4 to 1, okay? The runaway of hubcaps hitting cars and making more hubcaps, that's the chain reaction or collision cascade that we think about as the debris problem. I'd like to suggest that that's only a very small part of the problem. It's the thing that determines the rate of increase of problem, but it's not the problem. The problem is that for each car and 4 hubcaps, there may be of order 200 pieces of shrapnel that are too small to track with current techniques, but they pack enough punch to disable a high-value asset, including DoD satellites and Hubble, and breach the space station, okay? And if you're going to talk about what the cost of orbital debris is, and eventually if you want to do something about it, the decision is going to be made on a basis of dollars. It's going to be allocating dollars to a program, okay? And it's going to be based on dollar-based figures of merit. So we have to start converting our discussion of debris into dollars per year loss before we get the decision maker's attention. What's the cost of shrapnel? Nobody knows, okay? We don't know how much lethal shrapnel there is in LEO. We have statistical measures using Goldstone and haystack radars, but we can't track them, and so we can't look at how quickly they decay and estimate how thick they are, and therefore their mass. And we don't also know, for most cases, there are some programs that have had the money to investigate how large an object it takes to disable their satellite, but most satellites are not designed with armoring in mind, okay? We really need to, in order to make rational decisions, and the current national space policy is really go out, march through the fog, tell us what you see on the other side, and then we'll decide on a national policy about what to do next, okay? The technologists are being asked to march through the fog and figure out what can be done and what it's going to cost. We really have to identify mature concepts enough to cost them, to identify which ones are really credible and cost, and what fraction of the problem can they deal with. We've got a variety of options for dealing with shrapnel. Okay, individual operators can tolerate it, they can armor against it, or they can fly in orbits where it's less of a problem. And in particular for observing constellations like Skybox and Planet Imaging, Planet Labs and others, flying low has real advantages. You can either shrink the aperture, you have to bring lots of propellant, but you can get the same resolution with a smaller aperture, or you can take the same satellite, add a propulsion module, fly below space station and get better resolution. That's very attractive, okay? That doesn't solve the problem for everybody else, but it solves the problem for them. There are other things that, realistically, LEO is a commons, and commons have to be regulated or they're overused, okay? Fisheries have to be regulated or they're overused. There are a variety of things that involve better tracking or wholesale removal, and I'll very briefly discuss a few of them. Shifting gears from the shrapnel to where shrapnel will come from, it's going to come mostly from car-car collisions. The hubcap car collisions also contribute, but most of the mass involved in collisions will be involved in intact object collisions. And rather surprisingly, the 2 collisions that we've got good data on, the 2007 Feng-Yung ASAT collision, which was intentional, and the 2009 Cosmos Iridium collision, which was not, those two events together have created slightly more than half the tracked shrapnel and probably more than half the half the tracked hubcaps, and probably moderately over half of the total lethal shrapnel of 50 years of activity in space. Okay, so collisions between intact objects is a problem. Altitude clustering of dead objects is the main source of future unintentional collisions. And as you can see, from 750 to roughly 1,000 kilometers, the altitude distribution of dead objects is very clustered, and the 2 largest peaks are almost entirely Russian, okay? U.S. has more dollar value assets at risk than anybody else, but the source of the debris is going to be mostly Russian, okay? This brings up the debris problem in the context of international agreements, the Outer Space Treaty and the 1972 Debris Liability Convention. This is one of the references on the bibliography page. It's really worth study. I think it was done very carefully, and one of the things left out, I think was really important that it be left out, and that is a definition of fault. Okay, if 2 objects run into each other, is there fault? Well, what they would have agreed on, explicit agreement in 1972 would be irrelevant now. Okay, it used to be the boonies. Now LEO is downtown. Okay, the traffic patterns, the parking fees, all that stuff is different now. And it was, I think, a very good thing to leave fault undefined. The real punchline on this is that a bilateral U.S.-Russian agreement seems both necessary and sufficient to deal with the key parts of the problem, okay? We don't need a UN-level agreement. Unfortunately, we're not on very good terms with Russia right now, but the debris problem will wait, okay? We will sooner or later deal with that problem diplomatically in order to deal with the rest of the problem. As it is now, the current rule, first step in the right direction, is you're supposed to deorbit your stuff or put it into parking orbit within 25 years after end of mission. That's really free parking for 25 years after you finish your shopping, okay? That's okay in the boonies, it's not okay in suburbia, and it's definitely not okay downtown, okay? You try to park in San Francisco in a parking structure, you're paying for parking while you're driving around inside the structure looking for a place to park. You don't get free parking while you're shopping, okay? We're going to be heading in that direction. And the question is, what will the parking fees be? And my take on it is that by participating in LEO activities, you're adding to the debris problem. If you're not willing to somehow pay to remove part of that problem, you're really telling the governments that this isn't yet a serious problem, okay? If the folks that are participating in degrading the commons won't pay to clean up their own new messes, other governments, other entities should not come in and clean up the old messes. Okay, that's an unfortunate, but I think true problem. Now, Eddie is, this is the commercial break, okay, for 2 slides. Eddie is a candidate that can actually do wholesale shrapnel birth control by removing cars, okay? That's not directly the shrapnel problem, but it's a way of preventing the shrapnel problem from getting worse. I could spend a lot of time on it, but what I will do is talk to how it gets used. Oh, this is unfortunately, this is how how we got into this problem, as over time, how we've added stuff, okay? Now, a dozen Eddie vehicles with a total mass of roughly 1 ton can deal with this 2,200 tons of debris by dragging it down to 300 kilometers, or by dragging a lot of it down to roughly 650 to 750 and collecting it in rafts. Remember, I started out by talking about about recycling stuff starting at space station. If you run out of stuff to recycle at space station, don't deorbit this stuff, collect it and drag it to station. Eddie can do that, okay? Conclusions. Decision makers need dollar-based figures of merit in order to make decisions. If we don't provide them, they will make guesses. And it's really better that the engineering judgment be involved in those guesses, okay? We not turn it entirely over to congressional staffers. The main basis is really dollar values, asset losses from shrapnel. One of the references on slide 18 is a paper by Kelso and others about Blitz, which is a Russian optical retroreflector that's smaller than a soccer ball, okay? It clearly was hit. If you read the paper, they're not plausible alternatives. It was hit by a small piece of shrapnel. Too lethal to take out too small to take out most satellites, but enough to take that out. We should be doing more on optical tracking. I think we can push the threshold down way below 10 centimeters. Laser nudging, high-powered lasers that pulse something and ablate a small amount of material and nudge something. You don't have to deorbit it. If you can deorbit a small object, you can nudge a large one to prevent a collision. So that's another option for shrapnel birth control. Conclusion 5, if LEO users won't pay to null out their own risk additions, it's going to be hard to talk governments into putting other funding into dealing with net removal. And finally, debris management is a very multidimensional problem. It's technical, it's economic, it's political, which is distinct, and diplomatic. And one of the key things is, this is a paraphrase of a famous statement by Winston Churchill, and he went on to say, perhaps there is a key, that key is Russian national interest. And I think that the same is exactly true. We have to eventually deal with the Russians to solve this problem. We have to come up with an agreement. Okay.
Yep. Next, we have Dr. Bob Hoyt, who's CEO and Chief Scientist of Tethers Unlimited.
Okay, thank you. So at Tethers Unlimited, what we do is develop advanced technologies for space and defense missions. And what we really love doing is trying to come up with practical solutions for really hard challenges. And right now, we're working in a number of different areas, such as developing techniques for using additive manufacturing to enable satellites to create very large antennas and arrays, developing a number of high-performance components to enable small sats to do the jobs of big sats. But where we got our start 20 years ago was trying to address the space debris problem by developing space tether, electrodynamic tether technologies to enable satellites to deorbit at the end of their missions. Now, to be honest, over most of that 20 years, that's been a very frustrating proposition, because for most of that time, we were trying to sell an unconventional technology to satellite programs that really didn't care, because they didn't have any requirement to do anything about their satellite at the end of the mission. Fortunately, or unfortunately, a few years ago, we had a couple of orbital collisions that kind of hit home the problem, and so the regulatory environment has changed, and these space programs are now being required to deorbit their satellites or otherwise dispose of them within 25 years of the end of their missions. Another change that happened for us was we realized that we had to stop trying to sell the technology that we really wanted to develop, which was a very high-performance electrodynamic tether system, and focus instead on what the customer wanted, which was basically, to be honest, just to be able to meet the orbital debris mitigation requirement with a bare minimum of mass, cost, and risk. So over the past few years, we've focused on the development of a deorbit module that we call the Terminator tape. And to be honest, that device is basically a box with some conductive tape folded up in it. Now, it's more complicated than that. A lot of engineering testing has gone into to make it very reliable and minimize its weight and impact on the spacecraft. But it's basically a box that you bolt onto the side of your satellite before launch, and when you've completed your mission, activate the device, the box pops open and deploys a conductive tape either above or below the satellite, and that tape does two things. One is it greatly increases the aerodynamic drag area of the system, and it also interacts with the Earth's magnetic field and the conducting ionospheric plasma to generate a small but still significant amount of electrodynamic drag. And those two drag forces combine to bring the satellite down much more rapidly than it normally would. So basically with the Terminator tape, what we're trying to do is use the space environment to help keep the space environment clean. And this is it's a very simple and we think elegant solution, and it's also very scalable. And so far, we've developed two modules based on this idea. On the right, you see the CubeSat Terminator tape. That's a module about the size of a drink coaster. And that's sized for CubeSats and very small nanosats. And just recently, we've developed and delivered the nanosat Terminator tape, which is a somewhat larger module sized for nanosats and small microsats. Now, the CubeSat Terminator tape, again, it's designed for CubeSats. And because on a CubeSat, the surface area, footprint, is a very precious resource, we've designed it so you can have solar cells on top of the Terminator tape device, and we provide an electrical feed through. It's a very lightweight device, only 85 grams, qualified to quite severe GEMSAT spectrum, 30 Gs RMS. And we have 2 of those units up on orbit right now on CubeSats, and we're currently waiting for those CubeSats to finish their mission and activate us so that we can demonstrate the operation. But our analyses and simulations indicate that this device will enable CubeSats to comply with the 25-year orbital lifetime restriction up to altitudes of about 1,000 kilometers, maybe even a little bit higher. The nanosat terminator tape, we just recently completed the development and delivered a couple of units to our first customer, the University Nanosat program at the AFRL. That is expected to fly on the PROX-1 and NPSat missions in 2016. And because the University Nanosat program is a little concerned about the potential for infant mortality in these student-built satellites, we're also developing for them a dead man timer and activation circuit, so it'll really be a purely bolt-on independent module, completely independent of the spacecraft that will, for hell or high water, will bring it down after 18 months on orbit. And the nanosat terminator tape and the activation circuit are all designed to fit inside the 15-inch light band separation mechanism. And the total mass of it is under 1 kilogram, 808 grams. So looking a little bit further towards the future, we're also looking at ways of doing active debris remediation. And we just got started on a phase 1 contract or grant from NASA's Innovative Advanced Concepts Program, NIAC, on a concept looking at a concept we call Wrangler, which its primary objective is to enable capture and despin of asteroids to make the asteroid redirect mission or space-based utilization of asteroid resources lower risk and lower cost. The basic idea is we use a deployable net that we originally developed about 10 years ago for DARPA to basically grab onto a rotating or tumbling asteroid, and then we deploy a very lightweight tether. It's about the size of dental floss, but several miles long, in between the rotating asteroid and the nanosat. And that long tether provides an enormous amount of leverage to drain angular momentum from the rotating asteroid, enabling say a 10 kilogram nanosat to despin a 1 million kilogram asteroid. And one of the things we're hoping to do in the next few years is to demonstrate this technique by demonstrating capture, detumble, and then eventually deorbit of an upper stage or other piece of space debris. So it's also applicable to active debris remediation. So those are some of the things we're working on. Thanks very much.
And now we have J.C. Liu, Chief Scientist for Orbital Debris at NASA.
I would use this presentation to quantify the orbital debris problem and to outline the challenges for environment remediation. So here we are looking at the historical increase of the biggest objects, object being tracked by the Air Force and maintained in the US satellite catalog. So we are looking at the number of objects as function of time. The top curve is the total. The population breakdown is represented by the 4 curves below the total. And the 2 recent jumps are due to the ASAT test conducted by China in 2009 and the accidental collision between Iridium-33 and Cosmos 2251 in 2009. And as you can see, from the very beginning, fermentation debris has dominated the environment. And here I just show you where the jumps were due to the two major events, and of all the objects, spacecraft in the environment, only about 1,100 of them are operational. And this chart shows you the mass increase in space. So we are looking at the historical increase of material in space. Again, the top curve is the total. The population breakdown is represented by the 4 curves below the total. Unlike the number distribution that you saw from the previous chart, the mass is dominated by launch vehicle, upper stages, and spacecraft. And from the trend here, the top curve, you can see that there's no sign of slowing down. And this is a very big, serious problem because as we continue to add more material into the environment, we will only fuel the potential of the so-called Kessler syndrome. So how much junk is currently up there? In terms of number, as I said previously, the biggest objects, about 10 centimeter and larger, those objects are tracked by the Air Force. And they track typically between 20,000 and 23,000 objects. But in addition to the big objects, we have additional radar and optical observations that indicate when you go down to the 1 centimeter level, the debris population is about 500,000. And if you go down to 1 millimeter level, the population is estimated to be about 100 million or so. But because of the high impact speed in space, even sub-millimeter particle, a particle as small as 0.2 millimeter could be a problem for human spaceflight or robotic missions. And in terms of the total mass, we have about 300 tons of material in space from low Earth orbit all the way to geosynchronous region. And of that, about 2,700 tons of material are concentrated in low Earth orbit, the environment below 2,000 kilometer altitude. So we just look at the historical and the current orbital debris environment. How about the future? The future debris population increase in low Earth orbit has been looked at by the IADC, the Interagency Space Debris Coordination Committee. IADC consists of 12 major international space agencies. And recently, we have a modeling study where we have 6 space agencies using 6 different models to assess the future population increase. And the results from those 6 models, they are consistent with one another, meaning even with no future explosion and the global 90% compliance of the post-mission disposal measures, including the 25-year rule, the debris population in low Earth orbit is expected to increase in the next 200 years. And we expect to see one catastrophic collision involving intact objects every 5 to 9 years. So this is our best assessment of the population increase in the next 200 years. So when we talk about orbital debris in general, there are 2 problems associated with orbital debris. The first one is, of course, the population increase. And the root cause of the population increase is really catastrophic collisions involving large and massive intact objects, rocket bodies, or spacecraft. On the other hand, the major mission-ending threat for the majority of the operational spacecraft comes from impacts with debris just above the threshold of the protection shields. So typically, we are talking about orbital debris between 5 millimeters and 1 centimeter in size. So these are 2 major problems for orbital debris. Therefore, the best way to address the orbital debris is to take a solution-driven approach to look at these 4 elements. The first is to look into a concept that could remove massive intact objects with very high collision probabilities. The second element is to look into concepts that could prevent collisions involving intact objects as a temporary solution. Now, this concept, this element does not address the long-term problem of the debris population increase. It only provides a temporary a solution to slow down the population increase. And to address the mission-ending threat for the operational spacecraft, we need to look into ways to remove debris between about 5 millimeters and 1 centimeter. And of course, we can look into advanced materials to better protect our valuable space assets. In addition to these 4 elements, what Dave talked about earlier, if there is a way to recycle the material in space for something useful, of course, then we need to look into that option as well. So here I would just want to, again, emphasize the key size regimes for debris removal. Here we're looking at the cumulative size distribution of objects in low Earth orbit. So we have the cumulative number as function of size per half a decade points. So these are the distribution of orbital debris in low Earth orbit, the size distribution. And when we look into the biggest objects in the environment that are responsible for future population increase, in general, these are big objects, millimeters or larger. So for large debris removal, we need to focus on objects in this size regime. And when your spacecraft is hit by a debris that's less than 5 millimeters, in general, you have some damage. But in most cases, the damage is not mission ending. And when you have a mission ending problem because of orbital debris impact, chances are you are being hit by a piece of debris about 5 millimeters and larger. And because the size distribution of the orbital debris in the environment follow a parallel size distribution, so that about 80% of the object larger than 5 millimeters, they are concentrated between 5 millimeters and 1 centimeter. Therefore, if we want to address the mission-ending threat to the operational spacecraft, if we want to remove small debris to better protect the operational spacecraft, then we have to remove objects between 5 millimeters and 1 centimeter, because that's where 80% of the problem is. And let's go back to the large debris removal. If we want to address the root cause of the future population increase, we need to remove intact objects that are very massive, that have very high collision probabilities in the environment. And we know what those objects are. We know their orbits. And here we're looking at the altitude versus inclination distribution of those potential targets. And they form concentrations in altitude and in inclinations. And we can actually identify what those objects are. The great majority of the objects, they belong to the Russian vehicles. So that's what Joe talked about previously. As we continue to move forward to look into ways to better preserve the environment, we need to work with the Russians closely to come up with a way to address those upper stages and retired spacecraft. And here are just some pictures of the vehicles that we have to address for large debris removal, the upper stages, and the retired spacecraft. Typically, they are more than 1 metric ton in terms of mass and could go up as high as about 9 metric tons. And here we're looking at the mass distribution. So we have the metric ton as function of altitude, and between 800 and 1,000 kilometer altitude, that's where the main focus of debris removal, large debris removal should be focused on. There are more than 1,000 metric tons of material between 800 and 1,000 kilometer altitudes. So just in conclusion, as we continue to talk about environment remediation, as we talk about the debris removal, here are the key questions that we have to answer first. What is the acceptable threat level? and what are the mission objectives for environment remediation, for large debris removal or for small debris removal. And what is the appropriate roadmap or time frame for remediation? Environment remediation is difficult and it is very, very expensive. Environment remediation will not become a reality until we have identified an economically viable option. And of course, as we continue to develop technology, we also need to address the non-technical issues such as policy, ownership, liability, and legal at the national and international levels. Okay, that's all I have. Thank you.
Thanks. What I'll go ahead and do then is wrap up this portion of it, and then I'll ask the panel members if they have any final remarks before we open it up for questions. And with that, I guess if I can get my slides up. Okay. What this reminds me of when people say, well, why in the world are you talking, somebody from USRA, why are you talking about space degree? What kind of background do you have? And this really reminds me about 20 years ago, I had just started a job at the White House Science Office and under the Clinton era. And I was called to the NRO, and I met with the deputy director. And at the time, the NRO was very highly classified, and I didn't even know the thing existed. And so the guy said, well, what makes you qualified to represent space at the White House? And I said, well, I've written 4 books on it. Oh, okay. So that shut him up. But what I didn't tell him, they were all science fiction books. And, and I was new to this because I was a laser physicist. So the point I'm trying to make here is that it's not really my job with USRA, but it's the time I spent both at Los Alamos running the space programs and also at Space Command as chief scientist there, that where this became one of the overwhelming problems that we had. So the hard part, you know, we've really talked now about the so-called easy part. That's the technology. I mean, there are a lot of great ideas, and what we used to say is that now all it is just an engineering problem, right? You know, I can say that as a physicist. So what do physicists view as the hard part? Well, first of all, publicity. Is orbital debris really a problem? We heard from JC that there may be over 100 million objects, a millimeter and below in size. And is that really a problem? After all, space is a pretty big place. But on the other hand, Space Command, when they only track that 20 to 22,000 objects that are 10 centimeters and above. And it's all the other stuff that we have to worry about. And what I'm going to show you on the next slide, and my final slide, is that we don't even know where those objects that we track, we don't really know where they are, and we can't accurately predict where they're going to be. And that's just mind-boggling. And who's responsible for all this? Well, you know the Defense Department is not going to touch this at all. And why is that? It's because of the anti-satellite publicity that they would get, that all you want to do is you want to put up a new weapon in space. So the Defense Department is not going to do anything at all to do this. They're just going to say, well, it's NASA's problem or somebody else's problem, and we're just going to live with it. I mean, it's closing your eyes, but that's the reality of it. And what I really think is going to happen is that we're going to have to go to some kind of government industrial partnership in this until either there is a real profit that's going to be made, and it could be anything from reusing the material, or it's going to be that we're just going to have some kind of value proposition where industry needs to move into this. But we've done this in the past. Government, if you remember, back in the 1920s, really underwrote the airmail movement in the U.S., which really led to, until commercial industry got on its feet to produce the airplanes, which made everything from the Northrop Grumman's to the Lockheed and Martin Marietta's back then, to building airplanes. We also did this with the supercomputing industry. We didn't have supercomputers back in the 1970s that were available commercially. Serial 1 and Serial 2 of the Cray 1, for example, back then, well, which is what's equal to about an iPhone right now, was really existed only at Los Alamos. But the government underwrote that until it became a commercial venture. And so that moves us then into policy. Is right now we have great pre-launch policy that's really not enforced, but what type of post-launch policy do we have, in the sense of how are we going to enforce things where people don't deorbit, and how are we going to bring the international community in this? Do we really want to fund, for example, a country for with technologies to be able to deorbit satellites, and then 10 years later have that country use it against us? These are real questions that are being used. For example, you know, if we would have funded the Russians 10 years ago, you know, they're never going to do anything against us, right? Well, you know how fluid that situation is. So with that, and this is my final chain, the point I want to make here, my final slide, the point I want to make here is that we have a lot of great ideas. We have policy that needs to be put in place. But what we need to do, though, is spend a lot of time on the first 4 objects of trying to find the space debris. And this is a typical, what is known in the military as a kill chain, except I've called it a mitigation chain here. Is first you've got to find an object, you've got to fix it, that is you have to identify it, you have to make sure absolutely it's what you think it is, you have to track it, then you target it, and then the engage part, that's the cool technology here, and then you have to assess what you've done. So why do I say that we have to concentrate on the first 4? Going back to my comments about those 22,000 objects that that Space Command tracks for the international community right now, most people don't know that that is a catalog of tracking. It is not a real-time tracking. That is, we try to understand where things had been anywhere from 6 hours to 3 days ago. Okay? So we don't have the capability, nobody has the capability for all objects to be able to do it in real time. And what about prediction on that? Well, because of the oblate nature of the Earth, because of everything from friction in the ionosphere to actually photon pressure that's reflected off of all places, Jupiter and Mars, if you can believe it, that actually affects the location of satellites. In fact, at University College London, they have just done work with laser ranging on GPS satellites that approve that photons reflected off of Jupiter and Mars actually affect the position of GPS satellites over on a daily period. And if you were to go ahead and add up the contributions to that photon momentum pressure, it actually gives you errors on the order of meters on where the GPS satellites are. And so these are phenomenal effects. We can't predict more than about 7 days in advance where things are going to be. And with that, we even have error bars of 1.5 to 10 kilometers on each of these objects. So this problem of being able to mitigate space debris is the techniques to do it are only part of the problem. And what you need to do is first you have to find it, and you have to know where it is, and you have to predict where it's going to go if you're ever going to stop the problem. One of the techniques that is currently being talked about right now is to use a multi-phenomenological approach instead of just using either optical or radar to go ahead and predict and find objects. if you can build up a database for each of the objects with different signatures, say just not optically, but polarizations, IR signatures, if you know the radar cross-section, then what that allows you to do is to use different sensors and task those sensors to go after these different objects. And why is that important? Well, it's important because right now we only use one class of sensors for each class of satellites. Mostly right now in geosynchronous orbit, we only use optical techniques. Why can't we use other techniques? So if we can do that, then we can drive down the time of when we detect the objects. We can bring it more into real time. And also what we can do is we can increase the accuracy to find out where these objects are. So once we do all of that, then perhaps we can go ahead and use some of these other mitigation techniques that we've been discussing in the past. And the bumper sticker that I put down here is that it's really an applied science problem. I know how tough engineering is. It's incredibly tough to do. But on the other hand, there are a lot of science problems, a lot of science questions that needs to be answered in this multidisciplinary task of trying to mitigate orbital debris. And so with that, I will ask the panel, do you have any last comments before we open it up for questions? And I guess, Bob, okay, Rob, Joe, JC, Dave, Kirsten, okay, boy, everybody's satisfied. All right, with that, we'll open up the floor for questions. Yes, sir.
Methods of tracking is optically. What are some of the other methods that are being considered? And yeah, leave it at that.
Right now, the typical way to track is with very small satellites. Very small optical telescopes. And what you're looking at is streaks on a photographic plate, which have now being used with CCDs. And those streaks are being compared to the catalog of what we think, of where we think these objects should be. And if those streaks are where we think that they should be, then you're given a thumbs up and said, okay, we know where this object is. Basically what happens is anywhere from 1 to 5% of the time, those objects aren't there. You don't know what happens to them, and so we lose those objects. And as a result, even though other objects are detected that are nearby, you can't verify for sure that those objects are really the same object, excuse me, that you lost. And so as a result, the entire U.S. Space tracking catalog has a percentage of objects that are unknown. And if you were to re-find an object, then you have to use other verification techniques, say with radar and cross-sections on that. Another technique to track objects are with radar. And right now, for example, the so-called space fence is just being, the contract has just been awarded. And with that, radar cross-sections are going to be used for another class of satellites. But the whole idea of using this multi-phenomenological, using multi-phenomenal, I can't even say the word anymore, to use things such as IR, polarization, other signatures to be able to uniquely identify satellites will allow the catalog to be able to move closer and closer to real time. And so when we say that orbital debris is a problem, that's right, it's a problem, but it's mostly a problem right now, not because of the numbers, but because we just don't know where everything is and we can't accurately predict where they're going to be. Go ahead.
So your panel could have a benefit from a spokesman from the Department of State, as there is an international work right now on code of conduct to minimize debris. And there is a state, There is a position for the US on that. But in the meantime, you have a rule, and you have people who do not abide by the rule within the US. You have NASA missions which must abide by the 25 years rule, and you have all the NewSpace community sending CubeSats which do not abide by the same rule. So are you just looking to the other side, or what's going on here?
For the United States, we do have the U.S. government standard practices for limiting the generation of orbital debris. For the NASA missions, we do have NASA technical standard and procedure requirements for NASA missions that they do follow. For example, the 25-year rule to ensure that they don't generate long-lived debris in the future. And for commercial satellites, we work with FAA and FCC, try to regulate the activities, make sure that everybody follows the same set of rules to better preserve the environment. And the Department of Defense, they have a similar set of requirements for the DoD missions as well.
I'd like to add to that. There are treaty requirements that the U.S. and all other spacefaring nations have signed that say that the governments, the signatories, are responsible for authorizing and continually supervising the actions of their non-government entities, okay? In the U.S., you have to have a regulatory agency assigned to do that before you can regulate it. And so the FCC, if you have to go to the FCC if you're going to broadcast, okay? And then they impose their translation of these requirements on commercial missions. If you want to maneuver, if you want to launch something, you got to go to the FAA, and they license. But there are cases where you could actually do things in space where neither, you may not be required to get a license from either of those. We don't yet have, FAA personnel told me, the FAA does not have authority to regulate things that happen in space, just the way up and the way down. If you need that license, they can regulate what they do in space, but they don't have the authority to get at you and say no unless you're going up and down, or down with something intended to survive re-entry.
Well, my comment is very simple. NASA is sponsoring CubeSat launches. They pay for it. They do not regulate what they are doing in that case.
The thing is that most of the CubeSat launches have been to space station, released from space station. They deorbit within months. Okay, so in fact, it is in NASA's interest, since they have the largest and most expensive target in orbit called the ISS, to have things kicked out at ISS altitude and decay faster than space station. That's a wonderful solution for NASA and industry, and I'm glad it's worked out that way. But if you want to maneuver and climb, it's a challenge.
So we also, in trying to sell deorbit solutions, we also have been very frustrated that so many DoD and NASA missions can get waivers on the deorbit requirements. So the approach we're taking is try and come up with simple and affordable deorbit solutions that are so affordable that they cost less than the lawyer fees needed to get the waiver. So that's the approach we're taking.
Go ahead.
On the tracking data, do you have any spectral analysis or reflectivity data on these objects that these small objects that you're tracking?
Yeah, there are some data that are available, but not for all objects, and that's really the problem in that. And in fact, the problem is so bad is that there is an average of 1 alert a day that's given to both government, international, and commercial satellite operators, that there is an impending collision. But we're not certain that there's really going to be a collision because of the error bars on that. And as a result, the commercial operators have gotten to the point where they are starting to ignore some of the warnings on that. And if some of these new techniques can be implemented in both discovering, finding, and tracking the satellites, there is enough evidence that that warning can be taken from 1 a day to once a month. And if that is true, then the amount of money that the commercial operators and government agencies could save by not moving their satellites is just incredible. So there is a monetary motivation for that.
The question I was going to, is there any way of identifying what these particles are, what they're made of?
No, it's purely position now, and what you're talking about is the ability to understand exactly, is it a part of a rocket body? Is it a part of a satellite that had been hit from a collision? And that means that you need more exquisite, not tracking, but actually an understanding of what the object is. And that's an even tougher problem.
I'd like to comment that in GEO, most of the observations are optical. In LEO, most of the money is put into radar, and that's for military purposes, and the military very understandably does not want to turn all their cards over. And so you don't even know what the threshold is. They will not publish it. They will not tell you how many objects they can really see, but you expect that it should be somewhat better than they're willing to publish. I think that the military needs are always going to have a distinct enough agenda from what we need for avoidance that we're going to have to get funding of some alternative agency or funding through some non-military agency to some internationally based hosted optical observing network to start tracking stuff accurately enough. I mean, if we're going to have one collision every 5 to 10 years between tracked objects, but we're sending out conjunction warnings once a day, you know that those conjunction warnings are like, oh, you've got a 0.01% chance of being hit. Oh, and if you want to miss that, you have to move a kilometer. Well, if they can say 1% is often, we've got a 1% chance of being hit, and you only have to move 100 meters, that's more actionable. Okay, we're never going to be, oh, only move this object next year because that's the only one that's at risk. There will always be error bars, but I think that we have to shift from a military radar-based warning system to a non-military, multi-continent-based optical observing system to get rid of, drive down the uncertainties. And how to fund that is a big question.
Well, I just want to add to clarify this point. Although Department of Defense, although they do not publish their most accurate data, they do use their most accurate data for conjunction assessment and provide the conjunction warnings to spacecraft owner and operators, both national and international spacecraft owner and operators. So they do use the best data they have and then provide the information to satellite operators and owners.
If that's their best data, I'm even more scared.
Go ahead, please.
Hi. What if I wanted to solve this problem by launching a high-power laser system into orbit? Would somebody stop me? I guess is my question. You know, you said that the military's hesitant, the government's hesitant to get involved, and there are obviously military implications, but if I wanted to start my own private company and...
Yeah, I heard about 9 presentations on laser debris removal concepts at the DARPA conference at the end of 2009. And most of the speakers' first sentence was, this is not an ASAT. Okay, I knew I could take a nap then because I didn't have to trust anything else they were going to say. Anything that can deal with orbital debris is likely to be at least a halfway sensible ASAT system. And that's why it really probably shouldn't be operated by the military. I mean, a garbage truck is a lethal weapon. But if it's driven by a mafioso enforcer, it's a different thing than if it's delivered by a bonded driver working and getting paid to clean up garbage, okay? I think that laser orbital debris is an interesting option for both ground-based pulsed lasers and space-based. It may be competitive, but it's going to have to be operated by a non-military organization. It's going to have international shutter control that oh, we've got some object going by, you can't use it for the next 2 seconds. And it has to be paid for somehow by the people that benefit from its operation.
Right now, that would be illegal, as it turns out, because of ITAR rules, international trade, and international arms.
We've got it's Leo's a commons. We have to deal with this as a commons basis, and ITAR complicates that.
Right. Next, please.
Yes. If I understood David Barnhart correctly, with regards to the Phoenix project, Mr. Barnhart, you're talking about keeping things intact, using intact pieces of debris, and then the cellularization, putting the small sats on and in order to make that useful again. Now, I'm wondering, and this is for the whole panel, to anybody on the panel to answer, what about, is there any possibility, any use of having some sort of a salvage yard? You have many, many tons of refined metal up there, having a salvage yard and using it in another way, perhaps remelting some of this metal and using it in some other form. And where would that, if that makes any sense at all, where would that salvage yard be?
Let me comment on that. 3/8 of the total mass in low Earth orbit, other than space station, is 81 to 83 degrees inclination, and it's 99% plus Russian, okay? 3/16 of it is in sun sync orbit, okay? If you want to do some collection, you want to do it in those inclinations, okay, at nodal coincidence, which is a messy problem. But then you want to get rid of the stuff you can't sell there, and then drag the stuff you can sell to the customer orbit. You don't, I think that's the kind of sequence you want. And the key thing is that to start this, you really have to work out a US-Russian deal, okay? The US ventures are likely to be the place to start, but they're going to want to use mostly Russian stuff. The way to start is with the stuff leaving space station, because it's the same kind of stuff, okay? It's surplus, and it's already where you'd like it, okay? So space station, Bigelow facility, maybe flying 100 kilometers away, there's something that's doing dirty stuff. But start there, and then go to the real ore bodies, the high inclination orbits that have most of the stuff, when the 10 tons plus that you can get at space station isn't enough for your appetite.
So quick, an alternative, and Phoenix was started, you used the word salvage, which is interesting. There is a nomenclature given to the orbit, which typically you can get rid of geostationary. It's called the graveyard orbit, or it's referred to as such, right? And it is far enough outside of geostationary orbit such that we're talking centuries before anything would ever happen, if at all, to come back to it. So that was the precept by which the first application for Phoenix was identified relative to the use of mass that may have value in orbit. Now, the other really important reason for that, and I don't take umbrage with what you said, Joe, but I think we need to be very cautious, is if you use the word salvage, and we even looked at the details from beginning to end about separating things in space from a space object that's up there, that very act may indeed generate debris as we think about it. So the very act of salvaging may indeed generate debris, which now you have to consider and think about very succinctly and very carefully. So especially if you're going to talk about anywhere below the graveyard orbit, putting masses there that you could do something with, because you will almost always introduce the possibility of additional debris, which then unfortunately goes back to a salvage company has now done a salvage, something positive from a legal standpoint and an economic standpoint, but you generated debris, which now potentially impacted somebody else, so now who's liable, and we're back into this cycle, right? So anyway.
So I just wanted to mention, as Joe said, I think the place to start is the space station, because that's where we have a facility and people who can do it. And I wanted to point out that NASA's SBIR program is already starting to invest in those capabilities through work we're doing at Tethers Unlimited, as well as a separate effort at Made in Space to develop a system for recycling plastics into filament that can be used for 3D printing. So, you know, it's a very small first step, but we are, NASA and we are starting to make progress on that.
Something that's generally not realized, the shuttle is regarded as was a hydrogen, oxygen main engines, et cetera. The shuttle actually burned more aluminum than hydrogen on a mass basis. The bright white plumes of the solid rocket motors is mostly aluminum, glowing aluminum oxide, okay? So if you can't do anything else with aluminum, you can burn it.
Go ahead.
So if you're a spacecraft operator and you decide to increase your shielding, do you have to defend an entire sphere, or does the threat come from preferentially certain vectors?
Mostly horizontal and mostly, in fact, the space station's solar arrays, if positioned straight on and up and down, would protect most of the pressurized modules from most incident debris. Okay, so it's not, you don't need 4 pi steradians, just mostly a half circle and even somewhat less than that.
Right. If you go to the NASA Orbital Debris Program Office website, we do have a model, engineering model called ORDM 3.0 that will provide the information you need to build your shields. Now, we give you the directionality information, we give you the impact velocity distribution, and other information that you will need to better improve the protection of your vehicle.
Thank you.
Okay, the hook is starting to come out, but we have 2 more questions, and if we can just keep it to about 2.5 minutes each. So, sir, go ahead.
Many of you mentioned the importance of getting the debris on the agenda of the policymakers, and I was wondering if there have been any estimates on how much we're spending actually on avoiding collisions and repairing collisions now, and how that cost could evolve in the future.
Anybody have any estimates?
I'm sorry?
Yeah, JC?
I don't know if that's buried deep in the operating costs of different programs. I don't know that anybody has ever said, okay, what is it costing us now operationally? I don't know that just in general, the first cost study that I know of was Bill Ayler's one in 2010, okay? I did a study that hasn't been published, but it's still accessible online. The question of relating debris to dollars, we need to make much more progress than we have, and that's the side of it that I haven't addressed, and I'd love you to address it.
Yeah, because right now it's probably taken more out of the 5% reserve that they have for housekeeping functions. But I haven't heard of any analysis on that.
Yeah.
Great question,
But
though.
all aspects of the problem, in order to be considered by decision makers, need to be turned into dollars. Because if we don't do it, they will, and they won't do as good a job. Okay?
So for our last question.
Yeah, this is a great way. The last question is similar to mine. We talk a lot about the high-value objects, high-value intact targets. What organization has the authority to just, place a hit on this guy and say $100 million, bring him down?
Nobody.
Okay.
Okay. The bibliography on slide 18 refers, among other things, to the Outer Space Treaty and the other related treaties. Read that carefully and go back and reread them every month for a year, because you'll find each time you think you understand it and there's some key thing you're leaving out. I mean, for example, liability associated with space objects goes with the launching state, okay? You can sell an object, okay, but the liability, if it comes back to Earth, remains with the launching state unless the other state damages it in some way, and then they share in it. It gets really messy, and it's worth understanding. It's also worth understanding the context that sovereign countries are very jealous of their sovereignty, and the treaties say very explicitly this is the treaty liability from state A to state B. Whatever happens from state A injuring their own citizens, that's their business. Okay.
So
the treaties be very careful to only talk about international state-to-state liabilities.
Just to clarify, you were talking about ownership?
I was talking about targeting a satellite and putting like a dollar value to bring it down.
Okay, so what was
assigning
interesting?
a price to a high-value intact satellite.
Got it. Okay, so when we first started the Phoenix program, the day before we did the technical kickoff, we had a conference called the Fostering Sustainable Satellite Servicing Conference, 2-day conference that was held at DARPA International, and the particular things we were trying to work on were the policy, legal, and regulatory, knowing full well that you had to have a parallel path that went with those particular attributes that are non-technical with the technical at the same time. And one of the biggest things that I can tell you, I've had many, many meetings at the State Department, many, many meetings with legal affairs through the various government agencies, was about if DARPA was going to do a demonstration, or even any government agency would do a demonstration to prove the construct of repurposing. From a technical standpoint, the best retired candidate assets were non-US. And the way to get at them is you have to get permission from the original ownership and of the launching state, which Joe talked about. There's the launching state, and the launching state may constitute multiple entities the way the treaty has been identified, which then means the government has to do a bunch of outreach to a number of external entities to do that. From a debris standpoint, that becomes a nightmare. How do you prove who owns what to go after it? So it is a valid question.
Well, thanks, David. Excuse me. So thank you very much. I'd like to thank all the panelists for showing up and really engaging. Appreciate that.
We'll go to our first networking break now, sponsored by Silicon Valley Space Business Roundtable. We will meet back here at 11:30 for Will Marshall, CEO of Planet Labs, keynote speech. Rand Simberg is signing books in the exhibit hall right now for his new book, Safety is Not an Option. And if somebody left a green flash drive here yesterday, we have it. So you can come collect it from us. Thank you.
So just let everybody know. Context is important, acknowledging work that was done. There is, as was identified by Kirsten, and there will be an arm wrestling match that will occur about whether or not this was a DARPA NASA-sponsored activity or a RAND study, because I've heard many different ones. The individual's name who's on this is Wade Pulliam. He was a program manager at DARPA. DARPA and NASA sponsored a joint activity that occurred with NASA. JC, Robert Johnson. It was really cool. I got a chance to go to it when I wasn't at DARPA at the time, but it is I wouldn't call it a seminal work. I thought it is a point in time, but it's really good. I'm acknowledging things that have been done by other PMs and folks at DARPA that I will draw upon to show and elucidate my story this morning. So from that, a problem that we are here to discuss, we all know it. It was sort of publicized as the K syndrome, runaway things that might occur. This is an actual chart that came from that report specifically. It also identifies the possibility to mitigate the potential runaway probability of multiple debris that occur. So you can see that in this particular case, up and to the right means things are getting out of control. What you want to do is bring that line down to the right if possible. So what the study recommended was, and this was just one recommendation, let me be very careful about that, one recommendation, hopefully NASA may have others, is if you were able to remediate 5 large objects in space per year or per some annum, that you might be able to stabilize the predictive probability of populations of potential things that would cause debris to affect that K syndrome approach. Right? So that was one recommendation. My job here is to get you to think differently. What if we could rethink the phrase remove objects to mass usage? All right? Okay, well, how? Well, you got to have some gimmick if you're going to do that. So let's see if we can get this to work. Please bear with me here. Biology shows a bit of inspiration.
biologically inspired.
So our key takeaways in this area include various passive methods are effective for small low Earth orbit satellites. Active methods are the primary means for eliminating debris in GEO, both for mitigation and remediation. And as I mentioned, the capture mechanisms are currently low TRL. The technologies we've been looking at, they need to be considered as part of a systems solution that includes space situational awareness. And then this mix of domestic and non-US organizations in the community are working on various technologies and concepts. So the bottom line is a lot of promising technologies, but there are really few, if any, high benefit, high TRL options that are ready to be infused into our work. This is just really a brief overview of the technology landscape, and there's many other components to the discussion. I look forward to discussing further.
Well, great. Well, thanks, Chris. Well, thank you. And next, we're going to have Dave Barnhart, Program Manager at DARPA. And by the way, what we're doing is we're running through the panel members right now so that we can give all of us an overview of our take on orbital debris. And then we'll open this up for questions after a quick panel discussion. And as Dave is getting ready, just want to say that this problem of orbital debris was really not taken seriously until about 15 years ago or so. And I can distinctly remember over 20 years ago, one of my colleagues in fact, he was a professor at the Air Force Academy, had actually done his PhD thesis on orbital debris. And at that time, it was something that nobody could even imagine that we would have this type of problem. So with that, David?
Okay, hopefully this will work. Great. Hey, thanks very much. Thanks, Doug. Thanks to the distinguished panelists that I'm on here. First and foremost, I work for DARPA. There is no official position on orbital debris. Please do not throw me under the bus by me being here. Second and most importantly, the disclaimer at the bottom says, shoot the messenger, do not shoot the organization the messenger comes from.
Successful mission operations. The other dimension that we tried to bound the problem was looking at primarily domestic technologies. Those are really most of interest to government agencies. We did keep an open mind and looked at other lower TRL technologies or international organizations working in this area if we thought they were particularly notable. In talking about technologies for orbital debris, you really have to kind of set up some definitions. So the definitions that we looked at, we adapted the definitions from a recent RAND Corporation study on orbital debris called the Catcher-Smith study. And so we defined debris mitigation as actions that slow or prevent the future growth of orbital debris, and debris remediation as actions aimed at reducing or eliminating the population of existing debris. Paired with that, we had to look at the method for debris remediation or mitigation. So we looked at active methods, which require attitude control. This increases the system complexity and requires additional mass and volume. We also looked at passive methods. So these rely on natural forces to accomplish deorbiting. So given those definitions, we had 4 potential categories of technologies that we looked at. So active mitigation, passive mitigation, active remediation, or passive remediation. You'll notice that last one is not up there on the chart because we didn't come across any technologies that met our criteria in that particular grouping. So in the area of active mitigation, the technologies that we examined are chemical propulsion and solar sails. So chemical propulsion uses propellant to move the debris up to a higher graveyard orbit or lower the orbit to where atmospheric drag can take effect and remove the debris. Solar sails, they use the effects of atmospheric solar radiation pressure to create thrust and propel an object either to that a graveyard type orbit or to lower its perigee and deorbit the object. There are some other propulsion technologies that we looked at, and those are in the active remediation category. So the organizations working in this area, they are mainly working on mid-TRL technologies. So in the passive mitigation category, we had several groupings of technologies. Some of my fellow panelists have some technologies in this area. Electrodynamic or drag tethers, those use kilometers long cables or a flat wire. The cable is conductive and uses the Earth's atmosphere to create a force that reduces the velocity of the debris. Moving on to mechanically deployed drag devices, these are drag sails and balloons. So a drag sail uses a lightweight, thin membrane to increase cross-sectional area, and then uses atmospheric drag to deorbit the object. Another concept is balloons, also uses a small amount of gas to inflate the balloon to a size of tens of meters. This also takes advantage of atmospheric drag to deorbit the object. Quite a number of organizations working in this area. They are working on mid to high TRL technologies. There are a whole slew of other organizations that are working on lower TRL technologies, so a lot of activity in this particular grouping. The third and last category is active remediation. The two kinds of technologies that we looked at are propulsion plus grasping. So this uses a satellite to approach the orbital debris object and then uses a capture mechanism such as bags, harpoons, nets, robotic arms, tentacles, tethers, or even tugs to grab the object and deorbit it. Electrodynamic propulsion with the grappler. This also uses a conductive tether to propel the satellite close enough to grapple the debris object and then remove it. So So what's particularly interesting about this area of technology are the capture mechanisms, but those right now are very low and not very mature. Low TRL technologies, they're not particularly mature as of yet. So the organizations working here are working on mid-TRL concepts, and there are many others working on lower TRL technologies.
All right, we will get started with the orbital debris panel now. As more satellites are entering low Earth orbit and space travel becomes more frequent, orbital debris has come to the forefront of our minds as an imminently worsening issue that seems to have no clear and easy solution. Technical, legal, and regulatory talent are banding together to characterize and design solutions for mitigating orbital debris in LEO. Please welcome our panelists, experts in these areas, and our moderator for the orbital debris panel, Dr. Doug Beeson.
Good morning. Hopefully everybody is awake enough to think about everything from policy to technical details here. But we're just going to go ahead and kick off, and we're going to do this alphabetically. We're going to have Kirsten speak first. And she's a very well-known program manager, and her bio is in the book as well as everybody else's. So Kirsten.
Thank you. I have some charts. Can we switch over to those? Terrific. So good morning. Given the range of experts we have on this morning's panel, I'm planning to give an overview of the technologies that address the problem of orbital debris. One of the key questions that was put to the panel was, what technologies must be developed to interact with uncooperative space objects? This question comes at the problem from the demand side. So the Tory group recently did some work to look at what technologies are nearing maturity and could be deployed in the near future. So we took more of a supply side look at the technology landscape. So our main purpose in doing this was to look for the low-hanging fruit in terms of the technologies that are most near maturity and could be deployed into industry. So in the next few charts, I'll give you a quick overview of our analytical framework and some of our key findings and takeaways. So we tried to bound the problem. Obviously, there are a lot of orbital debris concepts out there. We focused on mid to high technology readiness level technologies. We focused on those technologies that are 4 through 9, so tested in a laboratory environment through